Cool. So any questions before we jump into all of that? All right. So let's do a quick wrap up on 202. Oh, yeah. So 202, right? Basic struct node with 3 fields to it, and then you were doing an initialization routine, setting elements 0 particular values, and then setting the remaining elements in the array with particular values. And so it can look like this. Here's my struct node declaration. I went ahead and used a type def. You don't have to do this, right? But you can say struct space node, or you can type def it to some other name and then use that name. So if I didn't do this type def here, I would have said struct space node star, and then the name of the array that I'm passing. You can call it whatever you want. It's an argument to a function, so you can name it what you like. I named it uppercase LL for linked list. And then initialization of the first element is, variable name bracket 0 dot data dot next dot valid, giving those the specific values asked for in the assignment. And then to set the other values, I used a for loop. You can do a while loop. You could do 99 statements, but don't do that. A for loop lets me say, for I equals 1, I less than or equal to 99. That tells me it's going to do 1, 2, 3, 4, dot, 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 98, 99. Right? And those are exactly the values I want. I want to start from and include 1. I want to end with and include 99. So a for loop lets me nail that down right here in the for statement. But you can do it with a while also if you prefer whiles. And then for each of those indices from 1 through 99, right, I use LL bracket, that index bracket I, and set the data next and valid fields as specified. And then there's no return, so I could either just say return semicolon, or I can just fall off the end of the earth here, and the function returns. So that's 202. Okay, that was your init function. 203 is basically going to be another part of PA1. It's your get node function, with a few differences from PA1's get node. So let's look at the README for that. It's the same struct node, okay, and you have to refer to PA1 to see the details of this. And your get node takes an array of struct nodes, and it's an array of 100 struct nodes, and it returns an integer. And your goal is to search through the array and look at the valid flags and find a node that's available, meaning the valid flag is 0. And the first node that you find, starting from the beginning where the valid flag is 0, that's the node whose index you want to return. So return that index. But it's possible that there are no nodes available. It's possible every node has a valid flag of 1. In that case, you're out of memory. And so you return a flag, which for here is just return 0. In PA1, it's myNull. And remember, index 0 is your sentinel node. Your sentinel node can't be used to store anything except the sentinel node. So get node should never return the address of the sentinel node. Right? It's looking for a place to store a new data node. So the return from get node should always be at least 1. So if it returns 0, that tells us something went wrong. That's our error flag saying, hey, there's no memory space. All right. So write the get node function, build your own test program, run that. When you're ready to assess, compile it into an executable with the test bed ODP203.0 and assess it. All right, and this is related to part of PA1, in particular to this function called getNode. So it describes this internal function you're supposed to write called getNode. Looks for the next free spot in the linked list array by checking the valid field. The two differences here from ODP 203 are, one, in addition to finding a node where valid is 0, your getNode should set the valid field to 1. In other words, mark it as now not being available anymore because you're going to use it. And two, if you're out of space, don't return a 0, return myNull, which is equal to 0. But just to be consistent. All right, so any questions on 203?
So just to be clear, we're searching through the nodes node by node, correct? We're not searching the array itself, looking at the valid fields?
You're searching the array itself.
Okay, gotcha. So element 0, element 1, element 2, element 3, element 4, so on and so forth.
But do not begin with element 0 in this case.
Okay.
Because element 0 is not a data node, it's the sentinel node. So it's really just a for loop starting from element 1, search through until you find a spot where the valid field is 0. In that case, just return its index.
Awesome, thank you.
Yeah. Yeah, that's a key point, right? Normally, we only want to manipulate this as a linked list. Normally, we're never going to monkey with the actual array directly, right? We're going to start with the sentinel node, and we're going to follow from node to node to node. But this is a low-level routine, right? It's used to support the other routines that you're going to write for doing add and search and delete and so on. So this one actually works with the array itself. PA2, we're going to get rid of these functions, though. And we're going to use the operating system's version of these.
Is there any faster way to declare a struct node without doing int data, int next, int valid under every single function that we're going to use?
I would do it like that so that you can put a comment next to each declaration. But you could say, you know, int this, comma that, comma the other thing. But I want you to comment the heck out of this code. And that's easier if each field is declared on a separate line. There's ways you could make it even faster depending on how sloppy one wants to get. And eventually we'll talk about header files, which reduce how much typing you have to do also. All right, good. Other questions? Yeah, we'll talk about headers tomorrow, but that's perfect. All right, let's go through some more details of PA1. So we went through a lot of this on Friday, but it was at the end of class and we were kind of getting time crunched. So let me go through this a little more detailed and then go through the parts we didn't get to. So you know what a struct node is. We've been doing this a few days now. You're going to use a myNull, which you've defined to be the same as 0. You're going to use this anytime that you check the .next field. Or anytime you're dealing with what should be an index into your array. If you want to know if it's not an index, it's a flag saying you're out of space. Compare it to myNull, okay, instead of 0. That's important. Your list itself is an array of 100 struct nodes. Exactly 100 struct nodes, no more, no fewer. Okay. Since it has 100 struct nodes and list 0 is the sentinel node, we can store up to 99 pieces of data in this list. Alright, but that element 0 is not a data node, it's a sentinel node. Alright, and you're going to implement 5 main functions. Init, which, you wrote a version of for 202, which you call in the very beginning of your main program to create an empty linked list. Add, which inserts something into the list, and it should insert it so that the list is always sorted smallest to largest. Don't sort after you're done building a list and you want to print it. Sort as you're inserting, right? By simply inserting in the right spot. There's nothing in the add function about what to do if your number is already in the list. So my expectation is you're never going to call add with a number that's already in the list. So in your main program, before you insert something in the list, call the search function, see if it's in there. And if it's not, print your error message from your main program. And then just don't call add with a number that's already in there. So now add just returns 1 for success, 0 if it fails. Print takes the array of struct nodes and prints out the list in order. Delete deletes and search searches. So those are pretty straightforward. I think we might have touched on, I don't know if we ran out of time, I might have punted to the A section, this notion of an abstract data type. Right? So as an abstract data type, a list is a structure with which you can add things, you can search for things, you can delete things, you can print the things that are in there. And how that is done is an implementation detail, right? In this case, we're going to do this with an array of struct nodes, where a struct node has 3 fields, and valid means this, and so on and so forth. In PA2, we're going to do something totally different. Our struct nodes are going to look different, and they're going to mean different things. I could do this with a hash. I could do this with, something that makes calls to Notepad and forces a Control F to do a search. There's a lot of ways I could implement these 5 functions. The goal is that how I implement these should not change your main program. Right? If I decide to implement this with some totally different approach, right, you shouldn't have to rewrite your main program in response to that. So an abstract data type is this idea of a firewall between the caller of your functions and the implementation of those functions. And the main program, the thing that's calling, should just see this uniform interface into your data structure. The way that you make that interface work, that's all your implementation details. That's all this low-level stuff. But ultimately, you're exposing your linked list through a set of 5 functions. Init, add, print, delete, and search. And your main program should really stick to these 5 functions to manipulate your linked list. And if your main program is doing things like checking list bracket 0.next, or things like that, you violated the notion of an abstract data type. Because list bracket 0.next equals mynull has nothing to do with what it means to be a linked list. If you go to another planet and you turn on the Universal Translator and you say, what is a linked list? They will tell you, well, it's a structure that you can add, you can delete, you can search, you can print. They're not going to say, and check element 0 of your array's next field to see if it's mynull to know if the list is empty. No. If you want to know if the list is empty, there should be a method or a function called, is empty, that returns a true or a false. So this is going to be a theme moving forward, and it'll make more sense as our structures get more and more complex. But we're going to want this separation between the code that we interact with from a main program, right, and the lower level code that makes that set of functions actually work. And that lower level code can change all the time, and the main program should not have to change in response. And if we adhere to this, it's going to make our coding easier, and it's going to make it easier to build code on top of other code. Yes, this is object-oriented programming. That's one of the key ideas of it. So this is all, build up to CSE223 in spring. All right. So lower level routines, there's at least 2 functions you're going to need to write to support these 5 functions. You'll probably need to write some other functions too. One is called getNode, and we just talked about that. The other is releaseNode. That's the undo for getNode. GetNode you call when you want to find a spot in the array that you can use to store a piece of data. When you delete a node, you no longer want that piece of data to be stored in memory. In other words, you want that spot in memory to be available for future use. That's when we call releaseNode. And we basically pass it the array of struct nodes and the index of the node we want to release. And it basically just sets the valid flag to 0. All right, let's look at a sample main program. Made it sticky. That's fine. I somehow made that page sticky so it appears on every desktop. That's okay. All right, here's an example of what your main program should look like, and yours should look very, very, very close to this. Okay, so you run your program, it prints a prompt, and it waits for you to type stuff. If you want to put out 1 or 2 lines in the beginning, that's okay, but don't clear the screen. Please don't print out a paragraph with 5-second delay from line to line to give the person time to read it. Please don't change the color of my desktop so that if I exit out, everything is purple or something. These are nice things to do, right, to enhance the user experience. But my fundamental, I'm the fundamental user here, right? And I'm going through 50 of these in a weekend, right? So I want to be pretty efficient in getting into here. So, if you want to make a user-friendly version and put that in your repository also, and in your README, you can say, try the user-friendly version for a better user experience. I can look at that. But try to stick to what the assignment asks. Oh yeah, making someone's desktop purple is the only way I know how to code. This is true. I actually don't mind when it turns purple. It actually breaks up the routineness of grading these, but that's not an invitation to cover my desktop with purple cows or something. All right, so I run main, it prints out a prompt. If I were to, type something it doesn't understand, or just hit an enter key or type a question mark, it gives me a short usage message. So here's a reminder of what the legal commands are with a typo in the word commands. I can insert a number, I can print the list, I can search for a number, I can delete a number, I can exit. Those are my only options here, right? And if I type something it doesn't understand, right, it should just give me that help message. All right, well, let's print our list, right? That's always fun. Hey, it didn't print anything. Why? Because there's nothing in the list. Okay, I didn't say empty list. I didn't say your list is empty, please insert something. Print an empty line. Right? Because the print specification says what? It says print the list in order on one line with the numbers separated by spaces. Well, there's nothing to print, so it, printed nothing on one line. All right. So let's insert something. So let's play with factorials. So I'll insert a 24 and a 120 and a 720 and 6 is a factorial, and 2 is a factorial, and 1 is a factorial. Alright, so I've inserted 6 numbers into my list. Let's print the list. Hey, there's my first 6 factorials. Someone asked, what is your insert nothing? I don't know what that means. Oh, what if you insert nothing? If I just type I, that's not a legal command, so show a usage message. if I say I ha ha ha, that's not a legal command, right? So the I command should be followed by a legal integer. Okay, if the command does not fit one of these things, print a synopsis of legal commands. All right, so I've inserted some numbers I can print, and there's my list. I can print a bunch of times, and there's my list. What else can I do? I can search for a number. So is 24 a factorial? Yes, it is. Is 25 a factorial? No, it's not. I will not test this with funny numbers like 2.5 or 2.0, so you don't have to go too extreme on the parsing, okay? I will test it with, you know, search for ha ha ha, okay? But I won't force you to detect something like, you know, 25 point ha ha as an illegal. But it's easy to check for that, right? Just do the percent C thing after the percent %D that we did in 224. You can hard code ha ha ha. Yeah, backdoors are fun. All right. So I can search for a number, right? So is 500 a factorial? No. Is 720 a factorial? Yes. All right. Suppose I insert 500, right? And then I realize I lost my mind, and 500 is not a factorial, that shouldn't be there. I can delete it, right? I delete 500, it says success. And if I print, you know, it's not in there anymore. If I try to delete 500 again, node not found. If I search for a node that's not in there, not found. If I try to insert something that's already in there, it should say node already in list. Okay, so these are spec'd out in here in detail. So legal commands: insert a number, insert the number into the list in the correct order, provided the node's not on the list. If the node's on the list, say node already in list. If you're out of space, say out of space, otherwise say success. So one of 3 possible error message responses. P just prints the list separated by spaces. S searches for a number, prints either found or not found. D deletes a number, says either success or node not found. And X exits. Anything else prints a synopsis. So we're just going to keep, you know, printing a prompt, letting the user type something in, responding to what they typed. And exercise the heck out of your program. Once you get to the point where you think you're ready to submit it, play with it. Try to break it, right? Do random stuff. Just bang on your keyboard, you know. You can write a script that has a whole bunch of insert commands, right? Copy and paste it. Right? So there's a bunch of commands. Well, I'm just going to, you know, copy these by highlighting, and I'm going to Control-Shift-V to paste. And so now I've just added a bunch of new nodes. And if I try to do those again, they're all going to be already in the list. Strict parsing is great. I'm always happy with that. Right? So while you're doing this, right, you want to be developing this in pieces, testing it as you go, right? So get in the habit of making yourself like test files with commands that you can just copy and paste, right? You can redirect from standard in, but after you do that, your program exits. So you know, either make your arrays smaller than 100, or make a test file that tries to insert, you know, 98 things into your list. Paste that in, and then insert a 99th, make sure it works, try to insert a 100th, and make sure it says out of space. Right, so mess with this. And then X should exit. Good edge cases to test, right? Empty list, search for stuff. Empty list, delete stuff. Insert a single node, make sure you can print it, make sure you can search for it, make sure you can delete it, make sure you can't search for it after you've deleted it, make sure you can't delete it after you've deleted it. These are all things I'm going to run on your code, right? Empty list, total edge case. List with one node, sometimes an edge case. List with two nodes, sometimes an edge case. List with 3 through infinity nodes, another set of cases, but usually same behavior from 3 versus more than 3. When you delete to go from a list with one thing to a list with 0 things, that's a special case. When you delete to go from 2 things to 1 thing, that can be a special case, right? So you want to spend a lot of time debugging, and you want to get in the habit of how you're going to exercise this code. And so writing scripts, you know, or things that you can copy and paste from will help with that. Insert a bunch of things, and then delete them all. And delete them in different orders. Delete something from the middle, delete something from the beginning, delete something from the end. Do those when it's the last element, when it's going to leave a single list. Do it when there's more stuff in the list, right? Try to delete things again. Try to search for things you deleted. And after you've deleted everything, make sure you can insert one thing. Make sure you can make a list containing just a 0, because 0 is a special value sometimes, right? So by the time you turn in your code, if you've tested it and it's passed all of your tests, hopefully it'll pass all of my tests, right? And I just showed you a bunch of the things that I'll do, but I don't have a test script. I just go in there and I just start putting in commands. So really, really, really exercise your code and do it as you're developing, right? Don't finish your main program and suddenly find there's a problem in your print function, because that's going to affect a lot of other stuff. All right, X command exits. All right, so let's go through more of this code. So that's your main program, okay? Deliverables. So your submission should include the following: all of the above routines. That's your 5 main functions that you're going to call from main, and the 2 support functions, get node and release node. Okay, I need to see all 7 of those, and they need to work as described in this write-up. I need a main program which uses, you know, fgets and scanf or whatever you need to let the user specify these commands and then do whatever it's supposed to do. Okay, so main program, lots of commenting. Okay, specifically in the beginning of each function, before the actual function declaration, so you're writing your get node function, right? Before you say, you know, integer get node parentheses, etc., curly bracket, I want a block of comments. And this block of comments should include the following information, okay? The name of the function, the arguments you pass to it, the meaning of the value it returns if it returns a value, what the function does, side effects, errors that can occur, anything else that you think the person who's going to call this function should know. Okay, this should generally be a few lines of comments. If your get node function comment block says get a node, you're not going to get points for it, right? What does the get node function do? Search the array of struct nodes for a spot that we can use to store a new piece of data. Do this by searching sequentially from index 1 until the valid flag is 0. Return the index of that available node as the function's return value. Side effects, the valid flag of that node is set to 1. That's important to know. ODP 203, you don't have to monkey with the valid flag. You're just looking for a spot where valid is 0. But for our PA1, the get node function also sets that node's valid field equal to 1. So that if I called get node again, it wouldn't give me back that same node, because when it gives me a node and says this is free, I'm going to use that node. So I want get node to mark that node as being in use. So that's the side effect. Possible errors. If there is no space left in the array, this function returns my_null, indicating we're out of space. Otherwise, the return value is the index of a free node. Okay, that's the level of commenting that I want before each function. Right? The goal is, if you're doing like bottom-up development, which is usually what we're doing at this level, you're going to be writing code that's going to call your getNode function, or your release node, or your search function, right? And how do you know what that function does, what arguments it takes, what it returns, what you should do with the return value, and so on? You look at the documentation, which is the comment block before the function. Okay, in addition, I want your code itself to be commented. So for I equals 1, I less than 99, I plus plus, if data bracket I dot valid equals 0, curly bracket, do some stuff. Better be a lot of comments in there. What is your for loop doing? Why are you starting from 1? Why are you going up to 99? Iterate through the list of possible data nodes, right? Why are we checking to see if this thing's valid field is equal to 0? See if this node is available for use. Why do we set valid to 1? Mark this node as being in use, right? Why do we return that index? Return the index of, this available node, and so on. So I want comment blocks in the beginning of each function. I want a comment on most lines of code, right? Explaining why you're doing this line of code. What does it mean? I also want a comment block in the beginning of your main program, and this has got to have your full name, the name of the class, the date, the assignment number, and in your own words, a description of what the program does. PA1 is not an adequate description. Linked list program is not an adequate description. An adequate description might be something like, programming assignment 1, a linked list program. This program creates an empty linked list and allows the user to manipulate it by typing in one-line commands. The user can add, search, delete, and insert into the list. You can put that in a README, but I definitely want it in a comment block in the program. But if you put it in a README, you can copy and paste that into your comment block, or vice versa. All right, and then I want a makefile for building the executable. If you break your thing into multiple pieces, make it a clean makefile. Don't just GC everything in the universe.c. Right? Make it very tactical. If your whole PA1 is a single, PA1.c, then it's just going to be, GCC-O PA1.c. All right. Put this into a GitLab repo named linked list 1 uppercase L's and add me as a reporter. All right. How is your grade assessed? I will download this at the deadline. If it's not downloadable at that point, that's a 20-point deduction. And you have 24 hours to make it downloadable, and I'll try again 24 hours later. Okay? And this is Ming the Merciless here, okay? If you forgot to add me as a reporter, 20-point deduction. If you used a lowercase l over here, 20-point deduction. Okay? This is serious. Because a lot of times, at a university, in a job application, when you're writing something for a client, you get one shot, and you really want to get good habits at dealing with these one-shot situations. So make sure, it's named linked list, I'm added as a reporter. I will let you email me until Wednesday if you want me to double check that I can download your repository. After Wednesday, I won't do that because otherwise I might get 50 requests Thursday night. But I suggest I hope you've got this under Git control already, and you're already pushing things out there. And hopefully, when you created the repository initially, you added me as a reporter. So you should already have this set up. And if you shoot me an email today and say, can you double check, right, I'll go in and I'll try to download. All right. So that's 20 points if I can't download it at the due date, and 0 points if I can't download it 24 hours later. I will send you a note on Canvas probably saying I couldn't download, and you'll have 24 hours to correct it. So make sure you check Canvas or have it set to notify you. If I cannot compile your code, if I cannot run your code, that's a minimum 40-point deduction. So you're starting with 60 out of 100 there. If you're not using myNull, every time that you look at a next field or you look at the return value from getNode, that's a 10-point deduction. Right? I really don't want you to hardwire 0 and compare the next field to see if it's equal to 0. I want you to use myNull. All right. If you're not using the node structure, if you're not making an array of struct nodes, if you're using perfectly fine linked lists but they're not following this assignment, that's a 0. Okay? The goal is not to create a linked list program. The goal is to implement linked lists using this approach. So you gotta be following this. Okay, that's the coarse grain stuff. The details: makefile 10%, getNode function 10%, release node 10%, initialize and print functions 5% each, add search delete 10% each. All right, and then your main program is 10%. So your code itself is 10. Plus 30 is 40, plus this is 50, plus release and get is 70% of your grade is, based on your code. Whereas the other 30%, 10% for a makefile, okay, and then 20% for coding style and comments. So that comment block before each function, 5%. Comment block in the beginning, 5%. Comments throughout, 5%. Some sort of consistent indenting style, 5%. When I say proper, what does that mean? I'm not going to give you an indenting guideline, okay? I'm not going to give you a style guide, but be consistent. When you have a function body, indent it. When you have the body of an if statement or a for loop or a while loop, indent it. When you define the elements of a structure, indent it, right? How much do you indent? Do you indent the curly brackets or the stuff inside the curly brackets? That's up to you. But I want to see indenting and I want to see consistency. Right? So that when I look at your code, the style supports understanding what the code is supposed to do and how it's structured. All right, questions on any of that? All right, let's launch into some pseudocode. So I think the print function is a good function to write early on, because once print is working, you can use that to help debug other functions. So let's think about the print function, and let me make a sample linked list over here. So here's my data, here's my next, here's my valid. And element 0 is the sentinel node. So it is always valid. And the next field is either myNull or it's the index of the first node in the list. And the data value we don't know or care about. So suppose we're making a list with 5, 10, 15, 20. Well, it could be that, here's where the 5 is and the 10 and the 15 and the 20. But that doesn't always happen. As you insert and delete things from your list, the order of these things will get jumbled up in your array. That's okay. And to make sure I'm keeping myself honest when I write pseudocode, I'm going to start with something that's not just 5, 10, 15, 20, but I'm going to jumble this up. So I'm going to make a totally synthetic arrangement of things here. Now let's say this is what my array looks like. Okay, what is this? Our Sentinel node has the index of the first node of our list. That's a 6. So this tells me a 5 is the first node in our list. The next field is 2. That's the second node. That's right here. So our second number is 10. The next field of that is 3. So index 3 has our third node, and that's a 15. There's our 15. The next field of that is a 1. That's the index of our fourth node. Index 1 has a data value of 20. That's our fourth node. The next field of that is my null, which means that's the end of the list. So this peculiar collection of values in this array of struct nodes corresponds to this linked list. There's a huge number of ways I could have filled in the values in this array that would still correspond to this exact same linked list. But my suggestion is when you're working on pseudocode and you're working on debugging, don't just do, 5, 10, 15, 20, because it lets you make mistaken assumptions and not get in trouble, right? If I make a mistaken assumption here, if I, for example, assume that the first element of my list is always at index 1, I'm going to get into trouble, right? And when you're developing and debugging, you want to get into trouble, right? You want mistakes to get you into trouble. Let's put it that way. And you know how to make a struct node. Make yourself a funny init function. Call it funny init, and have it create an array of struct nodes that looks like this, or whatever you want, and just array bracket 0 dot next is 6, valid as 1. Array bracket 1 dot data is 20, next is my null, valid as 1. Array bracket 2 dot data is 10, and so on. Just construct this by hand, right, so that you have a linked list with some interesting values and some interesting arrangement. And now let's think about a print function. So print, and we're going to pass it a struct node. I'm going to call it LL for linked list. And the goal is to print out the contents of our list in order. So here's a question. How do I find the index of the first node of my list? Because right now, it's down here at index 6 is where my list begins. How can I write some code that will get me to that index? LL bracket 0 dot next, someone says in chat. That's exactly right. LL bracket 0 is the Sentinel. So LL bracket 0 dot next is the first node. All right, terminology alert here. We'll be talking about things like the first node, right? There's 3 things at play here. There's this kind of abstract node, this thing containing a 5 that has an arrow after it, right? There's the element in our array of struct nodes, right? This thing containing a data 5 next of 2, valid of 1. And there's the index of the node. And we kind of are going to think about those 3 things as being equivalent. And at first we need to, keep them separate. We need to know if we're talking about the index, which is an integer, or the struct node, or this green 5 drawn on paper. But those 3 concepts will merge in our minds, and the more they're merged together, the more effective we are at writing code to manipulate data structures. So if we go strictly by the book, let me just make an integer called current and set it equal to LL bracket 0 dot next. Which means current's going to be equal to 6. By writing this out, by having all of this information here, it helps me write my next line of code. Because what I want to do is I want to print the data value of that first node. While current is 6, that's the index of this node in my array. So if I were to say LL bracket current, that's this entry in my array. And if I were to say LL bracket current dot data, that's this data value. And so if I print that, that'll print out my 5. All right, here's the magic part. How do I find the index of the next node in the list? You and I know the next node is 10. It's at an index of 2, but how do we find that 2 in code? So LL bracket current is our current node. That's a struct node. A struct node has a field called next, which is the index of the next node. So LL bracket current dot next, that's where the next node is. And so I'm going to set current equal to that. And in my mind, I'm thinking of current as the node that I want to print. So if I set current equal to LL bracket current dot next, and then I just go back up here, my print statement is going to print out, well, this is going to change current to 2. My print statement is going to print LL2 data, that's my 10. And then this assignment statement will change current to entry 2's next field, which will be a 3. And my print statement will print element 3's data value, which is 15. And it'll change current to element 3's next field, which is 1. And then when I come up here, I'll print 1's data value, which is a 20. And I'll change current to LL current next, which is my null.
Hey, Nick.
Yeah.
Hey, you'd also mentioned having a previous variable in there as well, right? So prior to changing current, you would set your current node equal to the previous.
There's no previous in here. For printing, all we need is the current.
Oh, okay.
Yeah, but when we do add, we'll throw in a previous.
Okay, gotcha.
Cool. All right, so final question. How does this loop stop? Because right now this is an infinite loop. I just drew an arrow that goes up unconditionally. And we just went through and we printed out the 5, 10, 15, 20. What can we use to know that we're done at this point? And there's different ways to do this depending on how you're writing this loop. But the way I've written this loop, I'm going to print the current node's data, and then I'm going to change current to be the next node. And after I printed this last node's data and I set current to be the next node, current ended up being my null. So if I put this whole thing in a loop, while current is not equal to my null, that should stop at exactly the right spot. Or you could break, you could do an infinite loop, and down here, someone said in chat, after I assign current, I could see if it's equal to my null, and if it is, I could break. Or up here, I could see if LL current.next is my null. One of the nice things about doing it like this is if I start off with an empty list, and I set current to the sentinel nodes next, well, if I have an empty list, this is my null, my while loop's never going to run, which means I won't print anything. So, you know, lots of different ways to code up the details of this, but this is the spirit of what you basically want to do. And this kind of thing we'll see again and again and again. This is how we move down the list. and this is how we're accessing a field in the list, and this is how we're knowing when we're done with the list. So we'll talk about add and search and delete tomorrow, and we'll write out some code for that, but we're going to see the same thing just repeated again and again in different ways. So I would say play around with this, think about it, and if you haven't started coding, start coding some of this up. Make yourself a bogus array, see if you can get a print routine working, and see if you can deal with these edge cases. All right, we will continue this tomorrow. I will catch you next time. Thanks.